In this video, we will define chemical potential in 12 different ways. But first, the most fundamental definition. UPAC defines the chemical potential mu of a species I in a mixture as follows. Mu sub I is delta G over delta Ni. Temperature, pressure, and the amounts of all other species are held constant. So G is a function of pressure, temperature, N1, N2, N3, etc. dG can be expressed as the sum of many terms. The dt term, the dp term, and then dn1 term, dn2 term, dn3 term, etc. Also, we can write dg is equal to negative s dt plus vdp plus the sum of mu I dni. Negative entropy is delta G over delta T. Volume is delta G over delta P. By holding all other independent variables constant, S and V are the total entropy and volume of the entire system. What if there's only one species in the system, and then over here the sum of mu I dni contains only one term, mu1 dn1? And what if this n1 is constant, and then this equation is reduced to dg is equal to negative s dt plus vdp? It's a simple expression of dg we have learned in the previous sections. What if the temperature and pressure are held constant? And again, this equation can be reduced. In a different way, dg is simply mu1 dn1. And mu1 is dg over dn1 under the specified temperature and pressure. In this case, chemical potential is simply the molar Gibbs energy of this pure species. But is mu always equal to molar Gibbs energy under constant temperature and pressure condition? The answer is no. In a mixture, mu is often different from the molar Gibbs energy under constant TP condition. We'll derive this, we'll calculate this a bit later. We have learned a few equations about U, H, A, and G. H is G plus Ts, A is G minus PV, U is A plus Ts. By using these equations and also the equation of dG in terms of chemical potential, we get three other equations for du, dH, and dA in terms of chemical potential, here, here, and here. And you can see this equation and the three other equations are very similar to each other. You basically just replace this negative 1, negative s dt plus vdp to just different expressions that we have learned before. Now, by looking at these four expressions, we have four different definitions of chemical potential. It's delta U over delta Ni, delta H over delta Ni, delta A over delta Ni, or delta G over delta Ni under different conditions. Over here, when we use U, make sure S and V are constant. When we use H, SP should be constant. When we use A, T and V should be constant. When we use delta G over delta Ni, then temperature and pressure should be held constant. This is the UPAC definition. We have more definitions for mu. If we use the triple product rule in calculus, delta U over delta N can be expressed as negative delta U over delta S times delta S over delta Ni. Just need to pay attention to the subscripts, and then we can see mu is negative T times delta S over delta Ni under constant UV condition. It's also negative T times delta S over delta Ni under constant HP condition. Again, we use the triple product rule to finish this derivation. So we can express mu as the variation of entropy with respect to the amount of the species. And also we can define chemical potential in terms of PVT, but I want to remind everyone the two most commonly used definitions of mu are the variations of A and G. with respect to the amount of the species. Delta A over delta N under constant TP condition, delta G over delta N under constant TP condition. It's just because it's easier experimentally to maintain a constant TV or constant TP condition. I'm going to show you how to express mu in terms of delta T over delta N, delta P over delta N, or delta V over delta M. However, those are trivial. Again, we want to focus on these two equations under a constant TV condition. Let's use A. On a constant TP condition, let's use delta G over delta Ni.